Swayam Prabha. Digital India. Educated India.
Welcome to lecture 4 of week 6 on NPTEL course on Muffler Acoustics. In this class we are going to talk about derivation of transfer matrices for conical mufflers. Transfer matrix for conical mufflers and or conical sections, I would say, something like this, where you probably know x1 and x2 and you know R1 and R2, and L would be x2 minus x1. Let us derive the transfer matrix, but before we do that, it might just be a good idea to talk about transfer matrix for any arbitrary thing in terms of generalized functions. So, let us assume that we have our function like this. So, this is written something like this, and g times the C1 is the arbitrary constant, this is C2, and Vx is something like this. So what happens now is that Px and Vx are then given by the following thing. It can be written in a matrix form like this: G11 times x and G12 times x, G21 and G22 x. So, it is written like this: C1 C2. Okay. Now, what we probably can do is that we need to eliminate the constant C1 and C2 and express everything, the state variables P1 and V1 mass velocities, with those at P2 and V2. So, this actually can be written in a compact form. Let us call this thing as a state vector S of x. So, S of x is equal to G of the vector C. So, what will this mean? This will mean S of 0 is equal to G of 0 times the constant C, where C vector is given by G of 0 inverse into S of 0. Probably write this as like this. Okay. Now, C can be substituted back in this equation to yield S of x vector is given by your G times x matrix. Remember, this was a function of x, although not written here explicitly, and S of 0 like this, and let us evaluate this at x is equal to L or any section, known section like this. Okay. So, we have got this. Now, what we need to do is that if we were to pre-multiply this with GL inverse times SL, so this would be unity matrix, and then multiplying this again with G0 would give us S of 0. So, your S of 0 would become like this. So, basically we have related the state variables at x is equal to 0 with those at x is equal to L. Here we have done that. So, the idea is that how do we use this generalized expression for the transfer matrix, to derive the transfer matrix for the conical chamber. So, conical section I would say. So, this is like this. T matrix is nothing but G of 0 into G of L whole inverse. This form would be particularly useful when the functions that we talked about here, these ones, all these are a bit tedious or algebraically complicated. Well, G11 and G12 for the conical section that we saw here, this does not appear to be too complicated, but when you talk about the expression for the mass velocity, there are a few extra terms here. So, that becomes a bit tedious. So, what I will do, I will not probably go through the entire derivation of the transfer matrix for this thing, rather I would just write down the transfer matrix for the conical duct, which has the following form: transfer matrix for a conical duct, a conical duct. So, where this is x2 and x1, x1 and x2 being x1 here and x2 here. So, this would become cos k naught L, where L is this thing, and minus 1 by cot k naught x1 into sine of k naught L. So, remember there is no mean flow that is considered here, and the next thing would be a little bit more involved. So, well, what I would do is that I will put this thing here. So, j times y2, that is at the section 2, x2 by x1 into sine of k naught L. So, this is related to the variables at x2. So, this obviously has a transfer matrix form like this: tilde, tilde, tilde and tilde. So, these two terms, so what are those? So, those are j times y2 into x1 by x2 into 1 plus k naught square x1 into x2 into sine of k naught L minus j times k naught into x2 times y2 1 minus x1 by x2 into cos of k naught L. We get this, and then what do we get? So, this is pretty tedious, algebraically this is a little tedious, and what do we do for the other term? That is the term that is present here. It is 1 by k naught times x2 into sine of k naught L plus x1 by x2 into cos of k naught L. Okay. So, this is a pretty tedious expression compared to the case for a uniform duct. From an engineering point of view, rather than working in terms of the hypothetical apex and all that sort of a thing, it is a bit more convenient to talk in terms of the radius at the two sections R1, R2 or D1 and D2 and the length L. So, where tan theta R2 minus R1 by L, and so this is D2 minus D1 divided by 2L. So, let me call 2 tan theta is equal to D2 minus D1 by L, and let me call this as the slope m. m is equal to 2 times tan theta into d2 minus d1. Let me have a look at this. What do we get here? P at let us say when we use these variables rather than x1 and x2, and we further make an assumption that, well, not as an assumption, it is basically your some relation x1 is equal to d1 by m and x2 is equal to d2 by m, and y2 is equal to y of L is equal to y at 0 into, or y at 1, I am sorry, y at 1 into d1 by d2 square. The idea is that if we use such a variable representation, we will get the following. So, this would become d2 by d1, where d1 is a smaller part, remember, and this is cos k naught L times m into k naught into d1 times sin k naught L, okay. And this is j times y1 into d2 by d1 into sin k naught L, and this would be j times y1 times d2 by d1 1 plus m square times k naught square into d1 d2 into sin of k naught into L minus j m times k naught d naught times y1 into your d2 by d1, and this would be 1 minus d1 by d2 whole thing into cos k naught L. We get this little tedious looking expression, although not very difficult, and m divided by k naught into d2 into sin of k naught L and plus your d1 by d2 into cos of k naught L. So, this would be your L, and so we will get this particular thing. So, this is the transfer matrix for a conical duct. Now, here we have your m, the slope, or the twice the slope. When m is 0, it is very easy to see that, you know, d2 becomes d1 when m is 0, right. So, in that case, this d2 is d2 by d1 is 1, and this term would go away, and so would all the terms pertaining here, here, and this would be unity. So, this would, I would cancel out, and you will get the familiar things, and similarly this is also 1, this will go away, and this will be 1. So, you get back your transfer matrix for a uniform duct, and that is the check of self consistency, what we have been always been insisting upon. Similarly, one can derive transfer matrix, exact transfer matrix for a exponential duct, which is a bit more simpler than the conical one, and then you know, exact analytical solutions do exist for a duct which is of a, you know, of parabolic and hyperbolic shape. So, what it basically it means is that if we have a duct whose cross section is varying in terms of a parabolic kind of a thing, or a hyperbolic kind of a thing, that is parabolic duct. So, it is something like this. This is just a schematic or a rough figure. So, you have this kind of a thing for a parabolic shaped duct, and how does a diverging or a converging hyperbolic duct look? So, it looks like like a diverging thing, similar to your exponential thing, but the way the profile varies is a bit different. So, the reason that I brought up this topic is because such systems, they have exact analytical solutions, although a bit complicated in terms of the Bessel function series or second function. So, I would suggest that interested readers to find out about the parabolic duct and the hyperbolic duct solutions for the one dimensional wave equation. It is algebraically very tedious, although exact solutions exist. So, we might just be wondering, why do we even do such things where obviously computational tools are available nowadays, and actually that will be the focus of our next lecture when we talk about the segmentation approach or a matricent approach, which is a kind of a numerical scheme to analyze ducts in which the cross section area gradually varies. So, what we will do now is that we will focus our attention back on the transfer matrix here and worry about the transmission loss calculations for such a thing. So, what we will do is that we will analyze the following configurations. Let me write it, let me make these things in a compact manner somewhere here only. We will consider just a duct here, and whatever waves are coming, they are just going here in this direction. And the other configuration we will be worrying about is sudden expansion. And so, this is 1, this is 2. Often we have things like this. Where this angle is given here. So, what we could do for such more complicated test cases is make use of the transfer matrix between, say, this section and this section, this section and this one and this one, then this one and this, finally from here to here. So, it becomes as simple as cascading or sequentially multiplying the transfer matrix for a given element. So, these are clearly uniform sections, where I have marked with the orange thing, these are diverging or a varying section, converging or diverging nature. So, one can figure out the transmission loss of such a composite kind of a configuration or a simple thing. So, what we are going to do in the remainder of this class is to derive perhaps the transmission loss for this system and this system, and make some general remarks, and in the next class we will do segmentation. So, let me open up the MATLAB for you. As usual, this is the MATLAB command screen, and the usual practice in MATLAB is to write function files. That is the most efficient way. So, what I have done quickly now is that all the parameters that I talked about, if you look at the screen here, this one, all this big matrix that we discussed in a while back. So, what I have done is that I have used this form of a matrix, and I have just simply written down the 4 pole parameters. So, T11 is basically the one that is highlighted here. So, not sure if you guys can see this properly or not. So, what I am going to do very quickly is that zoom it to the maximum allowable limit. So, perhaps this would be much better. So, T11 is your, I am so sorry, is this parameter. So, notice that the function starts with the this is basically a module. So, here I am assuming a little bit background on MATLAB programming or any programming for that matter. So, we would need certain variables. So, variables pertaining to the computation of sound speed is what is being declared at the top, and then the sound speed is given by square root of gamma p naught divided by rho naught, and then k naught is a variable wave number that is made available at the beginning of the program. That is the calling function, the function that invokes this particular module already has access to k naught. So, we have k naught. So, very quickly now T11 is basically d2 by d1 into cos k naught L. So, d2 remember was the diameter at the section 2 and d1 was the diameter at section 1. So, and L is basically x2 minus x1, that is the length of the axial length of the chamber, not the inclined length, axial length. So, this is what it was, and then m was also defined, I guess somewhere here, that is basically d2 minus d1 divided by L, and the characteristic impedance at the respective sections, section 1 and 2 are given by 1 and 2. Ordinarily I would write it, I would kind of comment it, and that is the advice that I would give to you students as well, but it is just written in a less time, this code. So, there were no comments, but anyways T11 is the first 4 pole parameters like we discussed, and T12 is your j times y1, that is characteristic impedance at section 1, into the ratio of d1 by d2 into sine k naught L, it was that thing. And now T21 is j into y1 into d2 by d1 into sine k naught L, and all the terms that follow. So, what I suggest is that you guys do some practice on your own, in the sense that the derivation, look at the notes, look at the screen carefully and copy this thing, and also you can refer to the monograph by Munjal, Acoustics of Ducts and Mufflers. On the second chapter, these expressions are given, and I guess you would also be able to derive on your own. So, anyhow, these are the 4 pole parameters what I have mentioned here, and they are nicely written into a matrix form. They are just variables at this stage, but now they have put in a matrix form, and this matrix is then passed on to the function that invokes this particular routine function. So, this t variable is the matrix which is for a given frequency and contains all the 4 pole parameters information. Now, have a look at this transmission loss. So, I kind of modified the code that I use for extend inlet and outlet element, that is why some things are commented out. So, these are the things that I would need at the calling. So, notice one crucial thing that I would like to point out is R inlet and R outlet. So, what it means is that, if you recall this section, let me get back to the screen. This was your D1, this one, and this was your D2. Now, once we have this, this R underscore inlet and R underscore out, they need not be the same as R1 and R2. So, it can be something like this, like I mentioned here. If this is R inlet and this is R outlet, but however, if they are the same, that is to say, if R inlet, and that is your, if you have a duct like this, then R inlet and R1 would be the same, and R outlet and R2 will be the same value. So, basically by cleverly choosing these values, we can analyze both the configurations using the same code. So, this is the area of the inlet pipe and characteristic impedance, and similarly for the other one, and conical matrix transfer matrix is given, is basically the function is invoked, and now comes the computation of the parameters, transmission loss value. So, this is something that we discussed in last week's lecture. So, transmission loss in terms of the transfer matrix parameters, basically transfer matrix parameters. So, these are basically this one. Now, notice that y I and y f, that is your nothing but these ones. So, this is what is multiplied, y I is multiplied throughout. Now, clearly when y I and y f are the same, then this is just unity, this will cancel out. So, we can do a whole lot of things, and then finally these parameters and transmission loss, then this function is invoked by the main calling routine, transmission loss plot conical duct. So, conical. So, what I am going to do is that minimize this and perhaps get back to the old thing, say 24 font, and so let us see configuration with, say, the inlet pipe is 100, that is basically, let us analyze a configuration in which let us have a look at the screen here. So, we are analyzing a configuration where this diameter is 100 mm, all dimensions in mm here, what I am writing on the screen, but I have divided by 1000 to make it in meter there. So, this is 200 mm, this is your 300 mm length, and so that is what is highlighted here, 200 mm and 100 mm length here, not sure if you can see, and 0.3 is the length, and 50 mm and 100 mm are the inlet and outlet diameters, in which case we are considering 50 and 100, we are actually considering a configuration like this, exactly flush mounted. The waves come here. So, we are just trying to study the effect of flare on the transmission loss. So, once I hit enter, what do I get? I get this. So, basically its transmission loss is non-zero, that is important to know, it is very negligible. Basically such a flare would introduce almost negligible transmission loss generally throughout the frequency domain. By itself it is very inefficient. So, it has to be supplemented by sudden area expansion, those are much more effective than gradual area changes, is what I am trying to say. So, it has a peak, or it starts, it gives a maximum value at 0 frequency, but it then there kind of has a maximum, but it dies down very rapidly. Now, what I will do is I will hold this thing on, I will hold on just to demonstrate what sudden expansions can do for you. So, 100 mm. Now, let us have a look at the screen again, and let us analyze the following configuration, this one. So, here at the inlet and outlet section, the chamber has diameter 100 mm and 200 mm respectively, but inlet and outlet pipe diameter, they can be much smaller. So, they can be something like 50 mm. So, 25 mm is the radius at the inlet and also is the outlet as is the usual case. And let us use a somewhat different color, let us use the red color. Okay. So, we get the following. So, you see the dramatic increase in the transmission loss, there is no comparison actually. So, sudden expansion, the conventional chamber produces a much better performance, but in fact at low frequency it does go to 0, but then that is kind of completely offset by high transmission loss once the performance picks up. But and another thing that to be noticed is that transmission loss never quite gets to 0 even at the resonance frequencies where I am pointing here and then you are here and so on. So, this is quite different from the simple expansion chamber. Just to make the matters even more clear, so if I use a blue color just to distinguish between the next configuration that I am going to present, and let me say this is diameter, let me call this is 200 mm thing. So, you see, so this was a uniform simple expansion chamber, this was something like, let us get to the screen, and it was something like, it was like this. So, you see that produces a better performance, but then it also has dips at a certain frequency. So, conical chamber, gradually varying area chambers, conical being one of the cases, pretty much has a advantage that it can get rid of the troughs at certain frequencies. So, a clever way is basically to combine this into a composite structure like the one that I discussed, and actually one can also use a conical, there are things like CCTRs, conical concentric tube resonators. Let me just draw, although I can't analyze it right now. So, there are things like their configurations which are used in two wheelers. So, mufflers which are like this, they can be fully perforated, the length can be fully perforated or they can be partially perforated. So, that is a very interesting actually area of study. A person can actually do some good research using based on higher multidimensional wave propagation in such a system, especially when the flow is there. Of course, we are not considering any flow here right now, but the point I am trying to make is that these are called CCTR, conical concentric tube resonator. We will worry about that in the next week, but just as a teaser of a result, and actually you can line it with different things and do whole lot of things. So, there are lots of avenues for interesting work on this conical chamber, because this is most likely most commercially most popularly used conical shapes rather than other gradually varying area shapes. So, we will end the discussion for this class now, but in the next class when we meet, what we are going to do is that we are going to study some configurations which basically cannot be solved using analytical things that were discussed in this class. I mean, so for example, if you have an extended inlet and outlet, but with the outside being a conical surface, then what are you going to do? Analytical solution probably does not exist. So, one has to resort to a numerical thing like a segmentation approach or a matricent approach, and then there are short chambers. So, short chamber means the length L by D ratio, L being the length and D being the diameter, L divided by D ratio is much smaller than 1, typically about 0.2, 0.3 or so. So, for such chambers the axial wave propagation, that is probably not the way to go ahead. What we need to do is to change the direction of wave propagation along the diameter or perhaps the major axis of of the chamber. So, there are lots of interesting things. We will take up a couple of cases which are to be analyzed using numerical techniques like segmentation approach in the next lecture. Till that time, goodbye and stay tuned. I will see you in the next class.